Today we're going to be discussing or further extending our understanding around the concept of arcs. If you remember from our previous lesson, arcs are essentially portions or pieces that sit on the circumference of the circle. They're essentially the connection, the length, the distance between 2 points that sit on the circumference. What we're looking at today is kind of qualitating them a little bit more, talking about how we might have things called like minor arcs or greater arcs, these smaller pieces or larger pieces within a circle, and then how we can draw some type of congruency statements around them, drawing some comparativeness. So let's take a look down at our notes first to start off here. I already got a few things written down. First off, we have our circle O, the point directly in the middle. In this particular example, we're going to have two different arcs. We're going to have what we're going to define down towards the bottom as our minor arc of AB, and then we're going to have our major or our greater arc of BA or AB. Just these two different portions here. What I'd like to just help you out here with is just some coloring of these particular arcs. We have our small arc here, or a minor arc, and then we have our greater arc. You can always pause your video to stop and begin to copy down some stuff. All arcs themselves have some type of measurements associated with them. The terms that we're going to use today, we're going to refer to length, which is kind of like, as we described in our previous lesson, as like the circumference or the distance around the physical circle itself. And then we're going to use the term measure. And measure basically means like the angle that's on the inside, or as we called our central angle. This little guy right here. To kind of describe arc length, we're just going to talk about circumference. And when we're talking about circumference, we're talking about some type of distance measurement. Examples of things like that are going to be, feet, inches, centimeters, miles, kilometers, all that stuff. Next, when we're talking about our arc measure, we're referring to, once again, that central angle, this reference point, this almost theta, if you will. So our arc measure, we're going to say, measures the central angle. And the central angle that intercepts our circle. As noted in our previous lesson, whenever we're talking about an arc, we're going to have some measurement of length here, and we're going to have an angle. The way these two relate also have some value or some commonality with the radius length. But as we previously mentioned, we can use deduction or deductive reasoning to, in a sense, use 2 out of 3 of those measurements, a radii length, a length of the actual arc itself, and that central angle to find the other missing value. What I like to go down here along the bottom is talk about different types of arcs. All arcs have the same type of definition, that there are 2 points that exist on the outside of the circle, but we're going to have ways to kind of differentiate or apply an additional layer of verbiage around them. The first one is going to be what's called a minor arc. A minor arc, loosely described here previously, minor arc is, in this particular example, like AB, in that a minor arc is going to measure less than 180 degrees. If we're going to take a look at this example here on the right-hand side, we can say that arc AB, this portion just along this side here, would be an example of our minor arc. The reason why we know this is going to be considered a minor arc is if we look down here in the center with segment DB, we can essentially call this a diameter since it goes from one side of our circle to the other, but also intersects through the center point or center point of O, allowing us to define it as the diameter. Knowing that, we can see how this portion here is going to be less than 180 degrees as it doesn't go halfway around the circle or form essentially a semicircle. A greater arc is going to be a measure greater than or equal to 180 degrees. An example that we're going to see here is going to be something like AB coming all the way around. Might be thinking to yourself, how do we differentiate between the two? We have arc AB, we have arc BA or AB. Essentially what we need to do is whenever we're going to go at 180 degrees or more, we're going to use 3 letters in our notation. One thing that you might want to add down to your notes is that connotation or that direction. 180 degrees or more, we're going to have 3 letters. Lastly, the only other type of arc that we're going to have here is what we call our semicircle or semicircle arc. And as we've all seen before, the measure is going to be 180 degrees. All right, so question here for you. If you're going to have an arc that's going to be, say, AB is equivalent to 95 degrees, what is going to be the value of arc BCA? In this case, we're going to just basically take 360 degrees. We're going to subtract 95 from it, and we're going to have left a value of 265. You can play around with these numbers here, kind of dividing little different pieces up. Say you can find the value of DE because you know DB is 180 and you were just told the value of AB is 95, and then you can solve for like those missing portions as well. But let's take a look. You can flip your page or get another one set up here, but let's go with another option here. We got set up here for you, a few pieces of notes here, but with congruency we're talking about things that have equal shape, equal size. We don't necessarily use the word equal all the time. Remember, equals when we're referring to a measure, so they're kind of interchangeable. But with congruency, we're talking about kind of like two squares that look exactly the same. And when we're referring to equality, we're talking about two circles with a radius of 6 inches being equal to one another. But for two circles to be congruent, all that has to be true about these two circles is that their radii or their diameters are going to be equal. If their radii are equal, their diameters are equal, their diameters are equal, their radii are equal. And whenever you have that interchangeability, you're going to have two circles which are congruent. This example here, I just drew the same circle in two spots. The first one has a radius of 3 inches. Your second has a diameter of 6 inches. So we're just doubling it. We're talking about arcs though. Arcs is a little bit different when we're going to refer to congruency. We have an additional layer of information that we want to kind of touch on in a sense. In regards to the congruency of circles, what we need or what we have to know is that two circles have essentially the same radius or the same diameter. Diameter and radius, as we know, are both interchangeable, being congruent to one another. We're going to see how that comes about in a handful of different ways. What's most important here is that for us to dictate congruency of arcs, or that they have the same length, we're going to have to know that they exist on the same measure. That central angle, that pie shape, that slice shape, is going to be of the same angle. In addition to that, we need to know for a fact that these two arcs have the same radius or the same diameter. That kind of dictates them. So they're going to come out from the center point, extend out to our circumference, and they have to have the same radius length and the same central angle. Knowing those two aspects dictates that the two lengths around, or the length for that circumference, are going to be congruent as well. What I'd like to do next is take a look at some examples and some other ways that we can show some congruency associated with arcs as well. We slide down here along the bottom. I have another circle drawn out for us, another circle O. In circle O here, we know a couple pieces of information right away. We can see how we have segments QR as parallel to segment ST. Euclides came up with a hypothesis here, or a valid theory, and that he stated if two lines are parallel to one another and they intersect a circle, essentially what ends up happening is you have two arcs which are going to be congruent. If you look at the nice circle that I drew here right in the middle, we can see how these two arcs kind of intersect and land right, or sorry, these two lines intersect and land right here. And we have this length of, say, 1, 2, 3 of these evenly spaced lines. So if we have two parallel lines going directly through, we end up getting two arcs that are congruent. If we're going to notate this down on our paper, we're going to say arc QS is going to be congruent to arc RT. We also could say the measures are equal. We can put a little baby m in front of there. But without knowing the actual degree measures, we're just going to leave it as our congruency symbol. Okay. So now that we actually have some of these rules that we can use to define arcs with equal central angles and radii dictate congruency, arcs that share this sense of parallelism can dictate congruency, what I like to do is show you another example, or kind of something that's going to look more like a question. It's going to allow us to kind of piece together various arcs and find some semblance of congruency and values that we can add. This one's going to have a little bit more detail. We have what we can say is chord AB, C-H-O-R-D, as in one of those segments that goes from one side of a circle to another and does not necessarily need to intersect at our center point, as in, forming a diameter. So we have chord AB, we have a legit diameter EC, and we see that both of these are going to be parallel. Knowing that these two lines are parallel, the first thing that we can go ahead and say is that BC and AE, or arcs AE and arc BC, are going to be congruent. Considering in this example we know the actual numeric measurement of 41 degrees, what I'm going to write down here is that measure example, where we're going to be able to go ahead and use an equal sign for our arcs here. Similar, before we talked about congruency when we had those like wacky diagrams associated with angles, and we talked about like alternate interior and stuff like that. When we talked about just the shape of the angle, we use the congruency symbol. But when we actually had like minute data, like say one angle is equal to 55, then we applied that measure value. In regards to this angle here, we can see how this 41 can kind of allow us to work with central angle BOC. The same thing on the side here with EA. Realistically, what we're looking at for this measure of the arc is that it's kind of like an invisible line from the points itself. So this open value here, AE, we can kind of close in theory with this nice dotted line. The next thing is, how do we go about solving for some of these other areas? We can kind of see down here for EC, we have a semicircle. We can set everything equal to 180 degrees and solve for it. But there's another way that we can go about finding this particular value. Might remember, we can actually find measure of ED using our vertical angles. We take a look here, we end up having two lines or two segments which intersect, and we end up forming a pair of vertical angles. So if we had something like a proof, for instance, that's one of the values that we could, or descriptions that we can use to kind of build up an argument, say. Two additions along the bottom. We can see that if we're going to look for the value of AD, we can look towards the bottom of our circle. For instance, we can take our 108 we have along the bottom here, our known 41 from our vertical congruency statement, in addition to that AE arc of 41, which we knew due to the parallelism that exists between chord AB and diameter EC. In a similar fashion, if we want to look for AB, we can use that notion of 180 for our semicircle along the top here and subtract those two known values of 41 and get our remainder. In addition to that, we could add up going around the opposite side and subtract that from 360 degrees as well. In our last example, we have two circles. In this particular diagram, we have what are called two concentric or concentric circles. Concentric meaning cone with Latin as in the same. They both have the same center point here. And with these two concentric circles, they both have arc measures of that central angle of 85 degrees. My question for you is, theoretically, would these two arcs be of the same length? And to kind of answer this one for you, the arc lengths for these are not going to be equal. So we can say our arc lengths are not equal or congruent because they do not share the same radii. We're looking at this kind of like as a proof or something along those lines. We're going ahead and say, okay, we know they need to have the same angle, which they clearly do. As I mentioned, they both have that 85-degree angle. The next thing we need to touch on, though, is whether or not their radius length is the same. Since the radius length is not the same, you can almost imagine it as like stretching your arms out. Like your arm measurement for your shoulders is all going to be congruent with a length, or that distance that would, say, connect your elbows is going to be different than what would theoretically connect, say, your fingertips. That is your lesson for this particular section. Our notes for this area are a little bit shorter. You'll see your questions that you have configured in Google Classroom. Got a set of independent practice questions as well too. What I'd like for you to do is make sure to complete those and show your work associated with them and as much as you can, and then upload your work directly to our Google Classroom assignment. In addition, you'll notice for today that there is some homework assigned. As I mentioned in your descriptions from last week, what I'm trying to do is make sure that I'm not overburdening you with work, give you a little bit more flexibility. And with homework added, I'm actually taking away from your independent practice and exit ticket. So you're going to have roughly the same amount of work, but you're going to have more flexibility on your time. So whatever homework you have assigned there is going to be due Thursday morning by 8 a.m. What I think is probably a wise option for you is that considering you now have a little bit more time, that maybe your homework questions are going to be like a little bit on the harder side, is that say on Wednesday, tomorrow afternoon, during office hours, you could come in and ask me questions as well too, because usually on Wednesdays I don't have too many people. All right, once again, office hours 1:30 to 3:30. You can ask me anything you want. Just got to reach out. All right, bye.